Welcome. In the last class, we were studying what we can possibly learn by looking at the electromagnetic radiation from the sun. And what we saw was that the electromagnetic radiation from the sun peaks at around 5,800 at around it has an effective temperature of around 5,800 Kelvin, and if you look at the spectrum, it peaks at around yellow, and in the region around the peak where the bulk of the radiation energy is localized in frequency, it is well described by a black body Planckian spectrum with a temperature of around 5,800 Kelvin. That was the first thing. The second thing that we learned was that the radiation originates from a thin shell. Well, it originates from a surface, it effectively originates from a surface where the optical depth reaches unity. So, we are looking from here, and the radiation originates from a surface of the sun inside the sun where the optical depth is of the order of unity. So, it originates from a thin shell around this, and the thickness of this is extremely small. It is around 0.1% of the total radius of the sun, and this is called the photosphere. So, the photosphere is where the optical depth reaches 1. So, the radiation that we receive originates from here, and there is evidence in the radiation that the temperature of the sun increases as you go inwards. So, the temperature increases as you go inside the sun. So, there is evidence that the temperature increases as you go in. These were the three things that we learnt in the last class. Today, let us try to work out what the interior of the sun looks like. Okay. So, we start off by considering this to be a spherical mass distribution, some gas, okay, which is in hydrostatic equilibrium, and we have written down the fluid equations, if you remember, and in the situation which you use to describe hydrostatic equilibrium, the equations are quite simple. So, the equation, there is only so in hydrostatic equilibrium, the pressure gradient divided by the density should be equal to rather this plus the force per unit mass F. These two should be balanced. Okay. Now, the situation that we are dealing with, the force per unit mass on any element of this fluid is essentially the gravitational force. So, we can represent the gravitational force in terms of a potential. So, this is minus grad phi, where the potential satisfies the Poisson equation. So, inside the sun, the pressure gradient essentially balances the gravitational attraction of the material inside. So, if you consider this element of the fluid, the pressure gradient across this balances the gravitational attraction of all the material inside this sphere, okay, which is what is there in this equation. It is a self-gravitating system. Now, in order to solve this equation, we need to know what the density is. We need some relation. See, there are two unknowns, there is the pressure and there is the density. We shall start off with a very simple assumption. Our assumption here is that the density inside the sun is a constant. So, we are going to make the simplifying assumption that rho is constant. So, let us estimate the value of the density of the mean density of the sun, and we will assume that this value is there throughout. It is a rather simplifying assumption, but we can make some progress with this. So, this value of the mean density is the mass of the sun, which I have already told you the value, divided by the volume of the sun, which is 4/3 pi and I have already given you these values. So, we will assume that this density holds throughout the entire sun. Okay. And if you put in the values, so this is 2 into 10 to the power 30 kilos, this is 6.96 into 10 to the power 8 meters. I have already told you these values. So, if you put in all of these numbers, the density, the mean density of the sun comes out to be 1.4. Let me express it in grams per cc, grams per centimeter cube. Okay. So, the density of the sun we see is comparable to the density of water, right. For comparison, let me also tell you the density of the earth. This is for the sun. The density of the earth is around 5.5 grams per cc, centimeter cube. Okay, so it is roughly 4 times denser, the earth. Okay, so the density of the sun, the mean density is comparable to that of water, and you might naively think that this is some kind of a liquid, but it is not so. This is mainly made up of hydrogen, and the temperature inside is sufficient, temperature and the density inside is sufficient to ionize the hydrogen. So, this is essentially a plasma where you have the charge, the protons and the electrons free inside this. The total charge is 0, but the protons and electrons are not bound to each other, they are free and they both behave like perfect gases. That is the situation. Okay. So, we are going to assume that the average density inside is this and it is a constant. So, with this assumption, let us go ahead and try to solve this equation. So, solving this equation is now with this assumption quite straightforward. We also have spherical symmetry. So, we will just multiply this over here, and what we have then is grad P is equal to, so grad P is equal to this, if I put it here, the minus sign cancels out, then I take it onto the right hand side. So, this is equal to rho into grad phi with a minus sign. Further, I could take a divergence of this, and we are led to the equation that del square P. Now, we have assumed that rho is a constant, so I can take it outside. So, I have del square of phi. So, this is equal to minus 4 pi g rho square. And we can write this in spherical polar coordinates. So, if I write it in spherical polar coordinates, what I have is 1 by r squared okay. So, this is we have to now solve this equation. We are working in spherical polar coordinates. So, we integrate this equation from the inside towards out, and if you integrate this, what you get is this will be r squared here, 1 by r squared d by dr r squared. So, this is the Laplacian operator in spherical polar coordinates. Okay. So, what we can do now is we can multiply this with r square and integrate it once. So, if I integrate it once, I will get r cube by 3. So, what this gives us finally then is r square dr p is equal to minus 4/3 pi g rho square r cube. Right. So, what I have done is I have taken the r squared there and integrated over r. So, that gives me r cube by 3. Then this I can again divide by r square, and so that will give me a factor of r, and then I integrated it. So, it will give me half r square. So, finally, the pressure is equal to minus 4/3 pi g rho, sorry, the r square, and this will not be 4, it will be 2. So, it is minus 2/3 pi g rho square r square plus a constant of integration k. Right, that is the pressure inside the sun in this simple model. Okay. Now, let me ask the question, what is the pressure at the surface of the sun? We have to put some boundary condition. So, we can measure things at the surface, and let us ask the question, what is the pressure at the surface of the sun? Now, obviously, the pressure outside is 0. So, the pressure at the surface of the sun has to be 0, that sets the boundary condition. So, at r equal to r naught, p equal to 0 at r equal to the radius of the sun. And we use this to determine the constant k. So, with this, imposing this boundary condition, what you have is that the pressure P is equal to 2 by 3 pi okay. Further, it is convenient to express this density in units of the total solar mass. Okay. So, this then can be written as 2/3 pi g m sun by 4/3 pi r sun cube, that is the density, the square of this, that is the density. So, we have 2/3 pi g rho squared, 2/3 pi g rho squared, and then we impose the boundary condition and we have a term. So, right. So, this is the pressure inside the sun. So, you can see that this all of this into 1 is the constant of integration, and this term into all of this is essentially just this. Okay. So, we have written it like this, and you can, it is now very clear that when the radius r goes to the radius of the sun, the pressure vanishes. Okay. Now, we will use this to calculate the pressure at the center of the sun. We want to calculate quantities inside the sun. So, let us use this to estimate what the pressure at the center is. Okay. So, the pressure at the center, at the core of the sun, according to this, then has a value. Let us see how much it comes out to be. So, you have 2/3 here, and in the denominator you have 16 by 9. So, a factor of 3 remains in the numerator, and here you have 16 and here you have 2. So, a factor of 8 remains here, and you have a factor of pi also in the denominator. So, that takes care of all the numerical coefficients, and then we have g m squared, the mass of the sun squared, by r to the power of, so here we have r to the power of 6, the radius of the sun, and here we have the radius of the sun squared. So, this is r sun to the power of 4. That is the pressure at the core of the sun, using this simple approximation assumption that the density is constant throughout. Okay, so, we have an estimate for the pressure at the center of the sun, and it comes out, it is expressed in terms of just the Newtonian, the universal gravitational constant, the mass of the sun, and the radius of the sun. It depends on just these 3 things, and there is a numerical coefficient outside. So, you now put in the values, we can put in the values of g, the mass of the sun, and the radius of the sun, and if you put in the values, we get an estimate of the pressure at the center of the sun, and this comes out to be equal to 14 newtons per meter square. I will ask you to yourself check this, just put in the numbers and just calculate this, check it for yourself. Okay. So, this is an estimate of the pressure at the center of the sun. Now, I should point out that in this expression we have made some drastic assumptions, and these drastic assumptions give us this result. Now, in this result, this numerical factor depends crucially on the assumptions that you make. If you had assumed some density profile, then this numerical factor would have been different. Okay. So, a more realistic estimate will give us some other numerical factor over here, but this part will more or less be the same. Okay. So, this is an order of magnitude estimate of the pressure. It is not a real, so you should not take this very literally, it is an order of magnitude estimate of the pressure. Say it will be within 10 or 100 times the actual pressure inside the sun, but it gives us some feel for what the pressure is. Okay. And this is the value that you get. For comparison, let us also estimate the pressure at the center of at the Earth's surface. Earth's surface, we know the pressure is equivalent to 76 centimeters of mercury, and we know the density of mercury. So, we can calculate the pressure at the surface of the Earth, and the value comes out to be of the order of 10 to the power 5 newtons per meter squared. That is the pressure on the surface of the Earth. So, you see there is a considerable, it is considerably larger, many orders of magnitude larger than the pressure at the surface of the Earth. Okay, it is enormous pressure that you have at the center of the sun. Basically the pressure is balancing is due to the entire weight, the gravitational is balancing the gravitational attraction of the entire mass that is above this. Okay, just like you calculate the pressure at the earth's surface, you take the air column above the earth and the weight of that is the pressure. Okay, similarly here you do exactly the same thing, except that the gravitational acceleration also changes with r, the density could also possibly change with r, we have not taken that into account over here. Okay. Now next we would also like to estimate the temperature at the center of the sun. Okay. Now to estimate the temperature at the center of the sun, that is, so we will assume that the we have pure hydrogen. Now we know that the sun is actually a combination of hydrogen and helium mainly. There are other elements, but they contribute insignificantly to the density. The density of hydrogen is also considerably larger than the density of helium. So we shall for the crude approximations here ignore helium and just proceed with hydrogen. Okay. So for any gas, if it is an ideal gas, then the pressure and the temperature are related as follows. It is equal, the pressure is the number density of particles into the Boltzmann constant into the temperature. So if you know the pressure, you can, and you know the number density, you can determine the temperature. Okay. Now the number density N is the mass density divided by the mass of individual particles. Okay. And if I have many species of particles, I have to then add up the contribution from each of these species. Now we write this number density of particles N as the density of the gas divided, so if it by the mass of one hydrogen atom. So if it were purely hydrogen atoms, this is the number density that you would have into this factor mu, which is the mean atomic weight of the constituents. Okay, so mu is the mean atomic weight, right. So essentially what we have done is we have written the sum rho I m I as equal to the sum rho I, this gives me the total density divided by mH into mu, right. That is what we have done. The total, if there are many components, the sum of each, the density of all the components is the total density rho, and the number density we have expressed like this. So it is the total density divided by the mass of hydrogen atom divided by the mean atomic weight. Okay, so we have just expressed this term like this, right. So from here we see that mu is equal to now the mean density is the number density of each species into the mass of each species, that is rho, divided by this is the number density of each species, the sum over that. So it is this is Ni. right. So, it is essentially the number density of each species into the mass of each species divided by the sum of the number densities of all the species into the mass of the hydrogen atom. That is what you mean by the mean atomic weight, right, in units of the mass weight of the hydrogen atom. Okay. So, this is the this is how you calculate the pressure, and here we are assuming that we have only hydrogen and the hydrogen is ionized. Okay, the temperature and the pressure are adequate to ionize the hydrogen. So, we are assuming that the hydrogen is ionized. Okay. So, if the hydrogen is ionized, then we have two species, we have the protons and we have the electrons. Okay. The mass of the electron we know is negligible compared to the mass of the proton. Okay. But the protons and the electrons contribute the same amount to the number density, right. So, from here we can say that mu, so in the numerator we have the contribution only from the protons, because the mass of the electrons is negligible. Okay. In the denominator we have the contribution from both the protons and the electrons. So, the numerator is essentially Ni, where Ni is the number density of say protons into the mass of the hydrogen atom, Nh let us say into Mh, the denominator is Mh, and here the electron and the proton density are same. So, we have 2 Nh. So, this comes out to be equal to half. Okay. So, for ionized hydrogen this is half. If you put in a fraction of helium, then it will get somewhat modified. Okay. The mean atomic weight for ionized hydrogen is half. So, we can use this. So, all that you have to do to estimate the temperature is you have to T is equal to so the temperature is equal to mH mu P by and you have to divide by rho into Kb. Right, this gives the temperature. So, we can now use the pressure that you have calculated to calculate the temperature inside the sun, and we can use this to calculate the temperature at the center of the sun. So, let us take this and estimate the temperature at the center of the sun. So, you put in the values of so we know the density, we had just estimated it 1.4 grams per cc. You know the Boltzmann constant, the hydrogen mass of the hydrogen atom, and here you put half, put in all of these factors and you get the temperature. The temperature comes out to be equal to, if you use this, the temperature comes out to be equal to 5.8 into 10 to the power 6 Kelvin, somewhere over here. Okay. So, again do not take this number very seriously. The main point is that the temperature also will scale proportional to these factors, and it will have some numerical factor which could be off by a few say 1 order or so. Okay. So, the temperature at the center of the sun, from what we have estimated, is somewhere of the order of tens of millions Kelvin. It is extremely hot, which is adequate to ionize all the hydrogen. So, what I have told you is also validated here. So, inside the sun the hydrogen is ionized, the temperature is of the order of tens of millions Kelvin, and it falls off to around 5800 at the photosphere. Okay. So, the temperature is around few million, tens of millions of Kelvin here, and it falls off to around 5800 Kelvin at the photosphere. So, this is the temperature gradient as you come outside. Okay, with these simple estimates, this is what we arrive at. Okay. Now, the radiation also then, let us see what kind of radiation do we expect at the center of the sun. So, if you have tens of millions of Kelvin, what kind of radiation do you expect at the center of the sun? Obviously, it is not going to be in the visible, right. At such high temperatures, X-ray is the most dominant kind of radiation. So, at the center of the sun, you predominantly have X-ray. Okay. So, at the center you have predominantly X-ray, and then this light propagates outwards, and by the time you are at the photosphere, you have lowered the temperature of the material and the radiation, and you have a temperature of around 5800 Kelvin. Okay. So, now we have also studied radiative transfer. So, let us now take a look at the propagation of this radiation from the center of the sun to the outside. That is the next thing that we are going to look at. Roughly, let us try to get a rough picture of how the radiation comes from the center of the sun to the outside. Okay. So, that is the next question that we are going to look at. And if you are looking at the propagation of radiation, now this radiation is going to scatter with matter, and the matter that we have here is essentially protons and electrons. These are charged particles. So, so electromagnetic radiation interacts with charged particles, we know that. So, there is going to be scattering of the radiation from these charged particles. Okay. And this scattering, in general, there will be energy transferred in this scattering. The scattering could be elastic or inelastic. Now, here we know that the radiation loses energy as it propagates through this medium. So, we know that the radiation, the scattering is going to be in general both elastic and inelastic. We also know this from other considerations. X-ray, when you scatter off electrons, you know that there is going to be Compton scattering, and which is inelastic. It can lose energy to the electron. You could also have inverse Compton scattering. Okay. So, there is energy transfer, and between the electrons and the radiation, and the matter, as the radiation propagates, it loses energy, transfers energy, exchanges energy with the matter, and it slowly comes out. Okay. So, we will have both elastic. So, the radiation will be scattered by the electrons and by the protons, right, by the ions both. The electron obviously is going to contribute more than the ions, but both of these effects are going to be there, and this will be both elastic and inelastic. Both of these will be there. Now, we know, so let us try to estimate the mean free path of the radiation inside the sun. Okay. And we know how to estimate the mean free path. We have discussed this quite some time ago when we were discussing radiative transfer. So, the mean free path, which we can denote by L, that is the mean distance between which the photon propagates freely before it encounters a scattering, before it interacts with the matter, right, is decided by where the optical depth becomes unity inside. Okay. So, what we have to do is consider a photon which starts off from somewhere and see where the optical depth becomes unity. When the optical depth becomes unity means it has interacted once, high probability it has interacted once. So, this is essentially the condition that the length, the distance into the absorption coefficient should be unity, or this mean free path we have seen is 1 by the absorption coefficient inside, right. We have seen this. And the absorption coefficient we know is the number density of particles into the scattering cross section of each particle, right. So, let us consider for making a simple estimate, let us just consider one process, the Thomson scattering, elastic scattering. Okay. So, for elastic scattering we know the Thomson scattering cross section. We have discussed this already when we were looking at the Eddington limit. This is in a problem. So, the absorption coefficient inside the sun we can estimate to be the density inside the sun, which we have already estimated, divided by the mass of the hydrogen atom. This will give us the electron density. We are assuming that the electrons will primarily scatter the radiation through Thomson scattering. In Thomson scattering what happens? Let me draw a picture. So, in Thomson scattering, this is my electron, the radiation incident on this is scattered into some other direction, and you can treat the electron as oscillating because of the incident electromagnetic radiation's electric field, and then calculate the dipole radiation from that oscillator. That is Thomson scattering. Okay. And Thomson scattering we can assume for our purposes it sends the incident radiation into some other direction, its frequency does not change, and the scattering cross section of Thomson scattering, we have already discussed, mentioned this earlier. It has a value for Thomson scattering, and it has a value sigma which is independent of frequency, and the value is 6.65 into 10 to the power minus 29 meter square. We have already discussed this earlier. Okay, this is Thomson scattering. So, the electrons inside the sun will scatter the radiation, and the number density of electrons is the number density of hydrogen atoms, same, because it is all ionized, singly ionized. So, it is the density divided by the mass of hydrogen atom into the value of sigma. This will give me the absorption coefficient, and 1 by this absorption coefficient will give me the mean free path. If you take these numbers, we have already estimated this we know and this we know. So, you take these numbers, put them in here, and this comes out, the mean free path comes out to be equal to, so the mean free path comes out to be equal to 17 into 10 to the power 3 minus 3 meters. So, it is around 1.7 centimeters. Okay, this is the minimum, this is the minimum scattering that you will have. In reality, the scattering could be more, the density could be higher towards the center. Further, you could have other inelastic processes also contributing, the Compton scattering, etc., and you would expect the mean free path to be actually smaller than this. Okay. And more realistic estimates tell you that the mean free path is around half a centimeter. This is around 1.74 times smaller. Okay. But we can take this and get some order of magnitude estimate. So, what do we learn from this? What we learn is that the photon from inside has to propagate over a distance which is 10 to the power 8 meters, 6 into 10 to the power 8 meters to get out, and then finally it comes to us. it can only propagate around a centimeter before it gets scattered by electrons. And as a consequence of this scattering, the electron that is propagating outwards will now be, after scattering, will now be propagating in some other random direction. And so the picture is that the photons which come out get kicked back and forth randomly many times, okay, at intervals, at these intervals, at roughly 1 centimeter intervals, and they have to keep on getting kicked around like this, and they make their way slowly out by such repeated kicks, random kicks. Okay, that is the picture. So, we will now try to estimate some other, let us try to make a more quantitative description of this. Okay. Now, we have studied radiative transfer. So, let us see what happens if you try to use radiative transfer to describe this process of scattering. Okay. So, we are going to assume that the scattering is isotropic. That is what we are going to assume. Okay, it is isotropic, and it is, so it sends off the incident radiation. So, we are modeling scattering as a very simple thing, elastic and isotropic. So, the scattering is being modeled as follows. There is some incident radiation. What the scattering does is that it sends it off in some random direction, the frequency remaining the same. Okay, that is our model, simple model. The real scattering process could be more complicated. It could be anisotropic. The probability of it going, the scattered radiation going in different directions could be direction dependent. It could also be inelastic, but let us just make this simple kind of thing. Okay. For this simple kind of a, with this scattering, we have already seen the absorption coefficient alpha nu is the number density into sigma nu. Okay. And we can then write down the radiative transfer equation. It is d by d tau, the specific intensity, is equal to minus I nu plus the source function S nu. Now, we know how to calculate tau, we just did it. What we have to now look at is the source function. Now, here in scattering, the scattered radiation that is scattered from this direction will be a source in some other direction, because the radiation that comes in goes out in some other direction. Okay. So, let us ask what is the emissivity, emissive coefficient, emission coefficient J nu. So, the emission coefficient we can calculate, that is the radiation emitted per unit volume in a certain direction. Okay. So, the incident radiation is I nu, and radiation from all directions will be absorbed equally. So, I have to integrate over all solid angles, and it will be going out equally in different solid angles. So, I have to divide by 4 pi and multiply this with n into with basically alpha nu. So, the emission coefficient is the absorption coefficient into just this factor, right. The radiation that is incident gets scattered into different directions, that is all. So, if you put in that fact, the emission coefficient and the absorption coefficient are related like this. So, the incident radiation from all directions, you average over that, and then it gets randomly distributed over 4 pi. So, from here it is clear that the source function, which is J nu by alpha nu, this is equal to the integral I nu by 4 pi. So, in the presence of scattering, the radiative transfer equation essentially looks like this. right. So, what is the difficulty with such an equation? Let us consider that I am trying to follow the evolution of the light along a particular ray, and I am looking at it at this point here, at this value of tau. Now, if I want to study what happens when I go from here to here, specific intensity from all directions over here, because all of these can get scattered into this direction. So, I cannot solve my radiative transfer equation separately for one ray. I have to simultaneously solve it for all different rays at all different locations, which is so this is an integral differential equation, and it is extremely difficult. Okay. Integral differential equation. Okay, this is extremely difficult to solve, and in general there are no, there are no general solutions available like we had when there was no scattering. In this case, with scattering, it is you have to make approximations and then proceed. Okay, so it is a very difficult problem. We shall not go into this. We shall analyze the whole issue in a kind of simple approach. The approach that we shall make is as follows. We shall model this whole thing, the whole propagation of this radiation, as a random walk. Okay. So, the incident, just look at any one photon. This is a photon like this, it gets scattered over here, and after the scattering it goes in some random direction, and then again it gets scattered over here and it goes in some random direction, let us say like this, and again it gets scattered over here and it goes in some random direction, could be here, okay. And in this process the photon moves around, that is the motion. So, it is called a random walk. So, at every step, at every scattering event, the direction gets shifted to another randomly chosen direction. Okay, this is called a random walk. Well, you can think of it as a drunkard who sets out from the pub and wants to go home, and his steps are all random. Okay, there is a probability that he will reach home, but it's a difficult thing. Okay, it's a difficult task. So, the photon here also starts off from the center of the sun and it gets kicked around randomly. There is a chance that one of the photons will escape and come out. Okay. So, we would like to now understand how the photon propagates under such a thing. To understand this, to analyze this, let us consider a random walk in one dimension. So, there is a one dimension x, you can call it x axis, and my photon starts off from here. In 1D, one dimension, it is quite simple, it can either go to the left or to the right. So, let us say that it goes one step to the left, and in my next step, so this is the first step, step 1, okay. Then in my second step, again it can go either to the left or to the right. So, it could, let us say it goes to the right once, this is step 2, okay. And each step it randomly decides whether it will go to the left or to the right. So, what we will do is, let us consider the position of the photon after n such steps, okay. So, we will call this the position of the photon after n steps, and this will be a sum of small x1, that is the first step, plus the position after the second step, third step, plus the fourth step, etc., all the way to xn. And these xn's are random numbers, they could either be plus 1 or minus 1, okay, or they could be plus some random number and minus some random number. So, if you now ask the question, what is the mean? So, random numbers can be generated, I could have many realizations of this, right. At each step I generate a random number and determine the new position. I can do this process many times and ask what is the expected position of the photon after n steps. Okay. Now, each of these are random numbers, so their average, which are equal probability of being positive or negative. So, the average of x1, average of x2 are all 0. Okay. So, the mean position displacement is 0. But if you ask the question, what is the mean square displacement? So, let us look at xn squared. So, this will have x1 squared, the mean of this, plus x2 squared, the mean of this, and n such terms, plus there will be 2 x1, x2, the cross terms. Okay. Now, we know that if you have two random variables which are independent, then the mean value of the product is the product of the mean values. Okay. So, this term is essentially the same as x1, x2, and it is 0. So, it is only these n terms over here which contribute. There are n such terms. Okay. And the magnitude, so this is the mean square, mean square displacement for one step, and this is going to be the mean free path of the photon, right. So, we know that the mean square displacement after n steps is going to be the number of steps into the okay. So, this is the mean free path. So, this I can write it as this, the mean free path squared. Okay, that is the mean free path squared. That is the typical distance between each scattering. Okay. So, now you see that the photon, so to cover a distance, okay, so let us see, to cover a distance our sun, the photon will need our sun by the mean free path, the square of this, these many steps, right. For the photon to come out from the center of the sun in steps of the mean free path, random steps of that size, the photon will need these many steps. Okay. And the time the photon takes for each step, so we want to estimate the time the photon takes to come out from the center of the sun. Okay. The time for each, this is going to be the time for each step. The time for each step is the mean free path divided by c. This into the number of steps, which is will give me the time the photon takes to come out. Okay, the photon does a random walk inside the sun, and finally at some time it will be out in the course of this random walk. So, this is the time that it will take. It has to take these many steps, and this is the time for each step, which we can write as the this is the time the photon would have taken if it travelled freely from the center of the sun out, and that time we know the radius of the sun is roughly 2 light seconds. Okay. The radius of the sun is roughly 2 light seconds. So, this will be 2 seconds into the ratio of our sun by the mean free path. Okay. So, let me remind you what we are discussing. If the photon propagates freely from the center of the sun outwards, it will take barely 2 seconds to come out, but it cannot propagate freely. It has to, it gets scattered. after traveling roughly every centimeter, half a centimeter or whatever, 1.7 centimeters, it changes direction. As a consequence, it takes much longer, and the amount by which it gets increased is basically the ratio of the distance it has to cover to the mean free path. Okay. So, if you now put in these numbers, we have estimated, we know both these numbers. If you put in these numbers, this comes out to be somewhere around 7,600 years. Okay, so it takes much longer for the photon to come out because it has to slowly diffuse out from the center through repeated scatterings. Okay. Let me also remind you that the estimate that we have made is an underestimate, because I have underestimated the scattering cross section. A more realistic estimate is 4 times this, and it will be around 30,000 years. Okay. So, if I take the right scattering cross section and the densities, the time it takes, the mean free path actually goes down, it is around half a centimeter, and the time it takes is around 4 times. So, it is around 30,000 years. This is the time the photon takes to come out. Okay. So, let me briefly remind you what we have discussed today. Today we have learned that the center of the sun is an extremely hot, it is tens of millions Kelvin, and the pressure is also extremely high. The whole thing is an ionized gas, and from the center you expect X-ray and things like that, X-rays essentially, and these X-ray get scattered repeatedly inside the sun and it slowly diffuses out. That is how the radiation from the center of the sun reaches us. Okay. Now, an important question that we have not addressed is what is the source of this energy? Right, this is something that we have to look at, and we shall go into this in the due course as we progress.